Hey guys, this is Drew, the SDSU EE tutor, and due to student requests, I've heard that some people are having issues with this problem, so being that I am a very good tutor, I figured I'd go over it in a video for you guys. So let's get started. Okay, so this is our problem, and given this transformer, we are supposed to show that the impedance from A to B, looking into the transformer, equals this equation if one of the dots on the transformer is reversed. Okay, so we're going to solve this first with both of the dots on top to make sure that everybody understands how we do the problem, and then we'll go back and flip one of the dots to change the polarity and see if we can get this equation in the top right corner. So the first thing we need to know are these transformer equations over on the side here. We need to use these to manipulate equations that we can pull from the circuit, and eventually we will get this expression up top. So first off, let's choose the way our currents are flowing in this circuit. Okay, so definitely we will have a current flowing through this inductor, and we can call that I1. Right? And then there'll definitely be a current flowing in this inductor, and let's draw this in this direction. We can call that I2. So then if both of these currents split at this terminal, then that means that the current going in has to be I1 plus I2. So we can say I1 plus I2 is going in this direction. Also, let's give these inductors voltages. Okay, so this can be V1 and this can be V2. Next, let's try and put this impedance in a simpler expression. Okay, so we can say ZAB is going to be equal to, well, typical impedance would just be V over I. So in our case, we can see terminal A is connected right to this V2, right? That's the voltage on our second inductor. So we can say that that voltage is going to be V2 divided by then our current flowing in from terminal A is I1 plus I2. Okay, so this is going to be I1 plus I2. So why do we get this expression here? Well, let's redraw this portion. So we are looking for the impedance entering these terminals, right? Meaning that on the left side of our circuit we've got some battery, right, and then some impedance going in, right? This is Z. So just in terms of Thevenin equivalence, this should be V Thevenin and this should be Z Thevenin. Alright, well, how do we solve this if we're doing a typical Thevenin equivalent? We would say V open circuit divided by I short circuit should be equal to Z Thevenin, right, which is really our ZAB. So in our problem, VOC, well, that's just the voltage at this terminal, right? That's going to be the voltage at A to B. And then short circuit, well, let's get rid of this. We said that the current flowing into A, we said that this was I1 plus I2. Alright, so that means that the current flowing in from this way has to be I1 plus I2. Okay, so if we were to do the short circuit test and short this down to there, Well, what would our short circuit be? Well, it's pretty easy to see that it would just be I1 plus I2 would be flowing down this way. Okay, so VOC, that's just VAB divided by I short circuit, which would be I1 plus I2. Okay, so that's where this comes from. Let's get back to the problem. So now we've established that ZAB is going to be equal to V2 over I1 plus I2. Okay, now we need to put these V's and I's in terms of N's, right? Because our final expression is in terms of ZL and N1 and N2. So let's manipulate these to see if we can get an equation out of them. So from this first guy, we can say that I2 is going to be equal to N1 divided by N2 times I1. Okay, so this is one expression. For our second equation, we can say that V1 is going to be equal to N1 over N2 times V2. Okay, and the reason why I chose V1 and I2 is they give us a term where it's N1 divided by N2. Okay, and the same thing with our second expression over here, V1 equals N1 over N2. Notice that the final answer we're trying to get up top, we've got N1 over N2. Okay, so that's why we did that. Okay, so now notice, yeah, this is good that we have I2 in terms of N1 over N2, and then we've got a V expression in terms of N1 over N2, but we can't just plug these in up here and get the expression we want yet. So we have another equation that we have to pull from our circuit. And that second equation, notice that this Z of the load, this is in parallel with both of the inductors right here. Okay, so that means that V1 plus V2 has to be equal to the voltage across this load, right? And what's the voltage across this load? Well, that's just going to be Z of the load times the current running through it, right? And the current running through it should be I1. So this gives us Z of the load times I1. And this is the expression that we want. For the next step, let's rewrite this expression in terms of just one voltage. Okay, so if we plug in this V1 to this V1, we're going to get N1 over N2 times V2 plus V2 should be equal to Z of the load times I1. Right, and this is Z of the load, this is a good thing, right? So if we go look up back at our equation, Z of the load, right? So this should be in our answer. So if we take out the V2 terms, we will get N1 over N2 plus 1, and this equals Z of the load times I1. And this is the last equation that we need to be able to plug in and solve the original ZAB. Okay, so now we have the equations that we need to solve our original ZAB. Right? And let's rewrite this guy right here So it's just in terms of V2. So V2 will be equal to ZL times I1 divided by, right, we're going to divide by this term, N1 over N2 plus 1. And now we can plug in these equations. Okay, so this expression is going to go on the top. Right, so that'll be in the numerator divided by I1 plus I2. And so this is I1 plus I2. But we know that I2 is just this expression. Right, so if we separate out the I1, this will become I1 times N1 over N2 plus 1. Alright, so now we're almost there, but let's drop this term in the denominator of the numerator down to the bottom. So if we do that, the numerator will only be Z of L times I1 divided by I1 times N1 over N2 plus 1. And then if we drop that term to the bottom, that'll be N1 over N2 plus 1. Or Z of L times I1 divided by I1 times N1 over N2 plus 1 squared. Okay, and then i's cancel out, and we're left with Z of L divided by N1 over N2 plus 1, that expression squared. That is pretty much what we want. Right, okay, but our problem said instead of having the dots both on top, it says what happens if we reverse the polarity. Right, so that means that the red dot, boom, now goes down on the bottom. Well, if we change the polarity, then this V2, this will become negative, right? So that'll be a negative V2. So then when you go back and you rework this problem, everywhere that you had one of your V's, it's going to become a negative term. So then if you work it out fully, you'll get the same expression, except the negative answer in the beginning will cause you to get Z of L divided by 1 minus N1 over N2 squared. So thanks for watching, and good luck on the test.